Hello and welcome back. Today we are going to look at models of substances beyond the ideal gas model. So, in the last couple of classes we have been looking at ideal gases which follow the ideal gas equation of state, and in addition to that we have seen how to deal with mixtures of ideal gases where if we know some of the properties we can calculate the remaining. For example, if we know the proportion of two gases and we know the volume and pressure, we can find out the temperature, or if we know the pressure and temperature we can find the volume and we can find out the Cp and Cv and internal energies, changes in enthalpy and so on. So, we have been dealing with ideal gases so far, and we will see what we can do in cases where the gases are not ideal. So, if we have an ideal gas, so we have the ideal gas equation of state, which is PV is mRT, where R of course is the specific gas constant, T is the temperature, m is the mass, V is the volume and P is the pressure, and we can divide V by m here, which gives us of course PV is equal to RT. So, if we are looking at a PV diagram and if we look at a specific kind of process where the temperature is constant, then essentially this becomes constant. So, then R is already a constant, we are looking at systems, so m is a constant. So, we get the equation as for an isothermal process we either get this or this, both of which are correct because m is anyway a constant, and this has the equation PV is equal to constant. So, if we are looking at a y versus x plot, we know that on a y-x plot xy equal to constant is the equation of a rectangular hyperbola. So, similarly on a PV diagram, PV is equal to constant represents a rectangular hyperbola, and we have these hyperbolic curves which represent the isotherms on a PV diagram for an ideal gas. This example shows an ideal gas which is nitrogen. So, we have values of xy equal to constant, and the constant here is essentially m into r into T. So, if I have a certain mass of gas, the gas is fixed, so r is also constant. If the temperature increases, then the value of this constant increases. So, I have PV is equal to constant, where a higher value of the constant represents a higher temperature process. So, what we see is if we look at these curves, as the value of the constant increases, the temperature increases. So, this for example represents a curve, an isotherm at 600 Kelvin. This represents an isotherm at 500 Kelvin. This is an isotherm at 400 and 300 Kelvin and so on. So, this is what the isotherms look like for an ideal gas on a PV diagram. So, if we have a process going from 1 to 2, this process is shown as parallel to the volume axis, which means it is a process which happens at constant pressure. So, I have an isobaric process from 1 to 2 if I look at this. So, as I go from 1 to 2, the pressure is constant, the volume and the specific volume both increase as I go from left to right on this diagram, and as I go from 1 to 2 I cut these isotherms, which means that my temperature is increasing. So, I see that going from 1 to 2 I have an isobaric process where the temperature increases and the specific volume increases. Similarly, if I go from 2 to 3, what I see is 2, 3 is a vertical line parallel to the pressure axis, which means that as I go from 2 to 3, the specific volume remains the same and the volume also remains the same. In going from here, the pressure drops from about 600 kilopascal to about, let us say, 300 kilopascal. So, the pressure is falling, and in going from 2 to 3, I am going from the isotherm at 600 Kelvin to the isotherm at 300 Kelvin. So, the temperature is dropping from about 600 to 300. So, I have a reduction in pressure and I have a reduction in temperature going from 2 to 3. And if I was to go along this isotherm 3 to 1 for example, then at 3 I have a certain specific volume, at 1 the volume has become smaller, at 3 I had a pressure corresponding to this, at 1 the pressure has become larger, but in both cases the temperature is the same. So, I would have an isothermal process with a high specific volume and a low pressure ending at a lower specific volume and a higher pressure, but with the temperature being the same. This would be the case if I had an ideal gas. What we saw is that an ideal gas has an equation of state of PV is mRT. So, what I can also do is plot these processes for an ideal gas on a temperature versus specific volume plot. So, I can plot on a what is called as a TV diagram. So, what I can see is over here T is equal to PV by mR. M is a constant if I have a system with a certain mass. R is the gas constant for the specific gas, which is also a constant. So, I have T is essentially some PV by some constant. Now, if I was to plot on this particular diagram, T versus V diagram, if I was to plot a constant pressure process, then P would also be constant for a constant pressure process. So, the isobars on a TV diagram would be given by this equation, where P is a constant, which essentially tells me that T is some constant times V. So, on a y versus x plot, which is what we are more commonly used to, an equation of the form y equal to m into x is a straight line with a slope of m. So, on a TV diagram, an equation of the form t is equal to some constant into x is also a straight line whose slope is c1. What I can also do is plot versus small v. So, I had here mr in the denominator. What I can do is I can write this as r into m, and this here is my small v. So, I have T is P by r, which is a constant, into small v, and if P is constant, so this P by r is also a constant here, and I have here a small v. So, I have on a T versus specific volume diagram, I have my isobars being straight lines with varying slopes. The slope is essentially given by this P by r here. So, which tells me that if the pressure is higher, then the slope would be higher, and this is what we see. So, here for example is an isobar on a TV diagram, where the value of the pressure is 500 kilopascal or 5 bar throughout this. If I go to an isobar with say 1000 kilopascals, which would be 10 bar, I would see that the slope of this line is steeper than the slope of this line. So, I can show isobars on a TV diagram in the same way, in a similar way to which I can show isotherms on a PV diagram and so on. So, what we also see here is we can look at even other processes on any of these diagrams. So, for example, here 1 to 2 is a process which is horizontal parallel to the specific volume axis, which means the temperature is constant. So, 1 to 2 over here shows an isotherm, temperature is constant. The specific volume is reducing from close to about 0.8 meter cube per kg to somewhere around 0.3 meter cube per kg. So, it is an isothermal process where we see that the specific volume is reducing. In that process, the pressure is going from 500 kilopascal, which is the intersection of this line and this line, to about 1000 kilopascal, which is the intersection of this specific volume and this pressure line. So, what we see is that the pressure is increasing and the specific volume is reducing, while the temperature is being constant in this process 1 to 2. Similarly, we can see what happens in process 2 to 3. At the state 2, we have the volume as being somewhere here around 0.3 meter cube per kg, that is a specific volume. The temperature at 2 is about 1000 Kelvin and the pressure is about 1000 kilopascal, and from 2 to 3 we see that the specific volume is constant. So, at 3 the specific volume is the same as it was at 2, but going from 2 to 3 the temperature has dropped from about 1000 Kelvin to about, let us say we are somewhere over here, let us say about 400 Kelvin or something like that. And in this process the pressure has gone down from 1000 kilopascal to 500 kilopascal. So, what we see is in the process 2 to 3 the pressure is dropping, the temperature is dropping, but the specific volume is constant. If I was to look at process 3 to 1, going from this point 3 towards 1, I am moving to the right, the specific volume is increasing. I am going upwards from 3 towards 1, which means the temperature is increasing. but the pressure is constant because both 3 and 1 are on this isobar. So, what we see is here we have an isobaric process where the pressure is constant, but the volume is increasing and the temperature is increasing. So, these are different processes which we can show on a TV diagram. In our definition of ideal gases, what we said is that Cp minus Cv is R, which is true. What we said is this R is a constant, the specific gas constant, which we get by dividing the universal gas constant by the molecular weight, and that is something which we have. Now, if we talk of what is called as a perfect gas, which we said is calorically perfect, then we said Cp and Cv are constants and they do not change at all, and then this is true. And in those cases, Cp, if I plotted Cp as a function of temperature, I would get a horizontal line, because for a perfect gas, Cp does not change with temperature. Similarly, if I was to plot Cv versus T for a perfect gas, it would also be a horizontal line, because Cv is a constant for a perfect gas and does not change with temperature. And what we would see is, since Cp minus Cv is R, if this was the value of Cp and this is the value of R, and then somewhere in between, if I take Cp minus the value of Cv, so I could show the value of Cv here, and this must be R, because Cp minus Cv is R. So, Cp is essentially Cv plus R. So, I can show this for a perfect gas, and that must be true. If I was to take ideal gases in general, we said that Cp and Cv are not constants. Cp is a function of temperature, so we can write it as Cp of T, which essentially tells us that Cp varies with temperature. Cv is also a function of temperature, so we can call it as Cv of T. So, we said that as temperatures go up, Cp tends to increase. As temperatures go up, Cv also tends to increase, but the difference would still be R. So, Cp is a function of temperature, Cv is a function of temperature, but the difference of these is still R, which is constant, which is essentially what we get from our ideal gas model. So, if I wanted to find out the variation in Cp and Cv, I could look at tables and find out how these vary. Now, if I was to plot Cv versus T or Cp versus T, I would get a graph of this kind. So, here I have Cv, this shows the variation, this curve over here shows, for example, the variation of Cv versus T from some point 1 to some point 2, it looks like this. If I was to take the area of this curve on the x axis, what I am doing is essentially integrating whatever is here under this curve. The integral of this would be integral of Cv dt from some temperature 1 to 2. If my temperature 1 is some reference temperature, this is from some T ref to some T. If I, for example, I call this as T and I call this as T ref, I get this. So, I would get integral of Cv, which is a function of T, into dt, and the integral of this would be essentially delta U. So, what I would get under this is the change in internal energy, because I am integrating Cv. If Cv was a constant, I could just write this as Cv times delta T, which is what we are usually used to doing. If Cv was not a constant, I would need to know the functional variation so that I can integrate it, but the integral would still represent the change in internal energy. Similarly, if I was to plot Cp versus T, it has some functional variation like this. For example, this is Cp versus T going from some reference temperature to some other temperature, or from state 1 to state 2. The area of this with respect to the T axis would be essentially integral of Cp of T into dt, which is essentially what we call as the change in enthalpy. And if Cp was a constant, it would be a straight line, and then delta H would be Cp into integral of dt, or it would just be Cp into delta T, because integral of dt is delta T. This is for a perfect gas, this is for an ideal gas. So, similarly, we see this is for an ideal gas, where Cv is a function of T. If Cv was not a function of T, we have what is called as a perfect gas, and then we would be able to write this expression instead. So, we see that that is how they vary, and even in this case, if I was to subtract out from the Cp, if I have to subtract out the Cv, what I should be left with over here is essentially R. This value would be R, and the integral would give me R delta T, because Cp minus Cv is R, even though Cp and Cv are varying individually. So, this is our ideal gas model which we are using. So, if we look at the equation of state, we have Pv is equal to mRT, or we have P small v is RT, which gives us Pv by RT is equal to 1. So, for an ideal gas, because Pv is RT, we expect Pv by RT to be equal to 1. This Pv by RT is what we call as Z, and we call it the compressibility factor. And this compressibility factor has a value of 1 for an ideal gas from the equation of state. But if we look at the value of this for a real gas, so for example, if we take actual gases, do experiments on them, measure the pressure, the specific volume, the temperature, and find out the value of the Z, we see that the values are not necessarily equal to 1. So, for example, for an ideal gas, we expect it to be equal to 1. So, we have irrespective of what the pressure is, and that is shown by this curve over here, this straight line, we expect it to be 1 irrespective of what the pressure is. For nitrogen at 300 Kelvin, we see that this value is pretty close to 1. For a range of pressures from about say 1 bar to about 40 bar, we see that the value is close to 1, which means it behaves pretty much like an ideal gas. For water vapor, even at a higher temperature of 600 Kelvin, what we see is that when the pressure is about 10 bar, the value is already deviating from 1. When the pressure is about 40 bar, we see that it is only about 90% of what it should have been. So, the value is about 0.9 instead of say 1. For CO2 at say 300 Kelvin, we see that at 40 bar, the value of Pv by RT, which is Z, is 0.8 instead of 1. So, what we see is that if we take real gases and find out the values of this Pv by RT, if we actually take the gas and do this experiment, the value of Pv by RT is not equal to 1, which means that these gases are not really following the ideal gas law. So, we expect them to be ideal gases, but in reality they are not ideal, and the Z tells us how far away from ideal they are. So, if we take this gas and measure it and find out Z to be equal to 1, then the gas is actually ideal, and then we can use the ideal gas law and we are happy about it. If we find that this value is not 1, then it means that the gas is not behaving in an ideal fashion. So, then the question is, what do we do? So, one of the things is, why is it not equal to 1? So, what we see is at low temperatures, there is intermolecular attractive forces between the molecules, and because of this, the pressure is lower than what we would have expected if the gas was ideal. Similarly, because the molecules attract each other, the volume which this gas occupies is smaller than what we would have expected it to occupy if the gas was ideal. So, the Z, which is the value of Pv by RT, where V is the actual volume it is occupying, if you have pressure and temperature fixed, tells us how close it is to ideal. So, if it is 1, it is ideal. If it is less than 1, the nearer it is to 1, the more ideal it is. The farther away from 1 it is, the less ideal this gas is. So, the question is, how do we deal with these kind of gases? So, one way is to use compressibility charts, and we will look at how to use them in the next class. Thank you.